Hi everyone, I just want to say hello and tell you that I'm excited because this week's experiments are really fun. We get to do a thin layer chromatography, and so basically we're going to have to go over some definitions and things like that, and so just to make things a little bit easier for you guys to visually see and kind of write things down, and then better presentation on my part, I'm going to go ahead and transition to the Notability app, so that way it's like me writing on a notebook, or I'm writing on a whiteboard, but I did want to just kind of show my face and say hello to everybody and tell you that this week's experiment's pretty fun. The topic in general is really important for organic chemistry because chromatography is basically the separation of two or more organic substances or ions by the distribution between two phases. And so it could be a solid phase or a liquid phase, or liquid, etc. Gases are included in chromatography, but basically there's two phases typically, and you're going to have a stationary phase, and then you're going to have what's called a mobile phase, or sometimes it's called a moving phase, and that's because it's moving, right? So there's tons of different types of chromatography, but what we're doing this week is thin layer chromatography. Bam, that's what that looks like. See this? It's got a piece of glass on one side and then a thin coating of silica on this side, and that would be our stationary phase because it's not moving. But what we're going to do is we're going to use something called an eluent that's going to travel up this, and that's going to be our mobile phase because it is moving. And so basically let's transition to that whiteboard, so that way I can give you a little depiction, a little drawing. They're going to be amazing drawings because I'm super good at drawing. I'm like, okay, so bear with me. I'll try my best to give you an understanding of how these organic molecules adsorb and desorb from this stationary phase on the TLC plate. Okay, and it's a general overview of chromatography as well. All right. Okay, so here we go. I wrote down the definition for you of chromatography. We are definitely doing thin layer chromatography. Chromatography is the separation of a mixture of two or more compounds or ions by distribution between two phases, one of which is a stationary phase and the other mobile or moving. And so this is something I already told you, but I just wanted to write that down for you so that you get that. You're going to replay the video 18 times to get it all. But also, I do want to remind you that TLC is a solid liquid phase type of chromatography, and this is what we're doing. The column chromatography, and TLC are very similar in that they have generally similar concepts, but it's just the direction of the flow of that mobile phase is basically going up for TLC, and then it's going down for column. Okay, so we'll explain that in a second, but their stationary phase is the same generally, and that's silica, which it could have some amount of hydration to it, so X amount of water molecules. This is called silica gel. Different silicic acid, I think, is another name for it. Al2O3. XH2O is alumina. Alumina. And this is basically like silica, but just different chemical structure, right? And so basically how it works, how does it work, you ask? All right, so how does it work? Well, it works by adsorption of organic compounds to the fine particles of alumina or silica, okay? And so adsorption to I'll put the solid phase or the stationary phase, okay? And so how is it going to adsorb to that solid phase? Well, it's going to do that using intermolecular forces such as London dispersion forces or van der Waals forces, the dipole. It's also going to do hydrogen bonding. That's how it can adhere or adsorb to the stationary phase. And then there's a couple other ones. Ooh, enough with the circles. Come on now. Coordination would be something, as well as salt formation. Okay, and so these last two are basically going to be the strongest way that an organic molecule can adsorb to the stationary phase, followed by hydrogen bonding, because that's the stronger intermolecular force, and then dipole, second strongest, and then London dispersion forces because they're weak sauce. Okay, so that basically means, since we're either hydrogen bonding or coordinating, that the more polar the functional group, the stronger the bond to the solid phase. More polar equals stronger. I'll put adsorption. Okay? And so basically, that's with respect, this is kind of the discussion with respect to the solid material and the organic material, but there is the mobile phase as well, right? And so solubility is really important. Solubility, and the solubility of the organic substance or molecule, that plays a role as well, and so is very important. And basically what we're looking at is like dissolves like, okay? And so what do I mean by that? Basically, the extent to which a solvent can wash an absorbed compound from a solid phase depends almost directly on the relative polarity of that solvent, okay? And so since silica and alumina are very polar, silica and alumina are polar, we need polar molecules are going to adsorb to them very well. That's why we say more polar equals a stronger adsorption, but that also means that we're going to require a even more polar solvent to kind of desorb those organic substances. So we need basically a polar eluent, okay, to desorb organic substance. I'll abbreviate that, okay? And so this is more or less going to be something like called a distribution equilibrium. And it's a distribution equilibrium of the adsorbent material and the solvent. Of adsorbent material and the solvent. Okay, and so what do we mean by that? Well, let's go ahead and paste this drawing I made already so I don't have to do it again all slow like. All right, pointing these things out. So we have a solid phase, that is silica or alumina, okay? And then we also have the organic molecule. So I just kind of, these are terrible circles. They're all supposed to be approximately the same size because whatever, right, in theory. But all of these are organic molecules, right? And so the ones that are directly on that solid are the organic molecules that are adsorbed and then these other ones floating around are the ones that are desorbed, and those are actually in solution. Okay, and those are in the mobile phase, and so they're able to kind of go back and forth. That's what this equilibrium is. So they're going back and forth, adsorption and desorption. Okay, and so what this allows us to do is very, very useful, and this allows us to separate organic substances. Okay, and so that's why chromatography is the separation of two or more organic substances. And so because the polarities of each molecule are very unique, they'll have adsorption rates and desorption rates at they're all going to be very unique. So very unique adsorption and desorption rates. And so since we more or less have a certain amount of the organic molecule present in solution, they travel down they travel through that solid phase at a different rate. And since they all travel at a different rate, what happens is it forms a separation of organic molecules. Okay, and so let's take a look at that. I got a super sweet drawing already prepped for you. It's lovely. So this right here is actually a column. Oh, sorry, I guess not the bottom part. That's a beaker, right? But what I've drawn here is kind of like a step 1, step 2, step 3. So right here we have the eluent. Let me do a different color. We have an eluent. Actually, let me use blue because it's cool. Blue. Eluent that's that liquid, or that's the solvent that we are using to kind of desorb the organic material. And then we also have our solid material here. And then generally a column chromatography is prepped in a giant tube, and we have sand here and then cotton here, and as well as a stopcock that allows the liquids to kind of drip out, and then we collect them in a little container of some sort, right? And so step 2, what's going on here? Basically what we did was we add the mixture of organic materials in here, red and black dots, on top of that solid phase, that stationary phase. And since they're all, usually we try and make it as concentrated as possible, so it's really thin, like rather than like this whole thing, maybe like just that whole thing. But the drawing is exaggerated so that it's more clear to you guys. And so since if it's more concentrated, then that means that they're all starting at the same starting point, and then it's pretty much a race down that column. And so they're all going to come out at the bottom, because that's basically they're going to travel through that eluent or in the eluent through the solid phase, and then they're going to come down into this beaker or like a test tube or something, whatever you collected it. Okay, so the point I'm trying to make is that since they all started at the same point here at the top, that's the same starting line, but they all had different rates of adsorption and desorption. That means that band 2 is going to be one organic molecule, and band 1 is going to be another organic molecule. So the red actually traveled down through that stationary phase a lot faster than the black dots. And so what that means is since the stationary phase is polar, that means that the red is less or even non-polar, and the black would be the more polar compound, because it was, remember, it's kind of like or as I stated above, the stronger the intermolecular forces, so like maybe the dipole or the hydrogen bonding, then the stronger the adsorption. And so it's basically going to be traveling through this column at a much slower rate than the non-polar compounds. And so what we end up getting is two separate bands, and we're allowed to collect them separately. And so we can get a beaker of red, and then we can eventually get a beaker of the black band 2. And that's why column chromatography is so important and so useful, and because you can go through all this work, and when you do an organic chemical reaction, nothing's ever perfect. You don't just put two things in and then get one pure substance out. Sometimes reactions don't go to completion. Sometimes they have side products, and so you can have not just two things, but maybe even like 10 things mixed together, and you have to figure out how to separate them. And so this is a very common method to do that in an organic synthesis lab. And before you actually do all the work that it takes to prep column chromatography, what you typically do is a TLC plate, because since they're so similar, you basically try it very quickly on a TLC plate, because it takes a small fraction of the time to run a TLC than it does to run an actual column. And so what you can do is test out, boom, 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 you spot your sample here, and then eventually let's say you have sample A, sample B, and sample C, and then A actually splits up into two bands. And well, let me get rid of B and C, because those are actually not relevant. Let's just leave it at this. So imagine this represented what was just explained above in the column chromatography. This is what it would actually look like on a TLC plate. So if I spotted that organic sample here, rather than placing it at the top here, and then I ran the solvent, this is the difference. Again, as I stated in the beginning of the video, the eluent travels up the TLC plate, whereas in a column we're traveling down the column. Okay, so what we see is that here's band 2 and then here's band 1, and notice how they separated on the TLC plate. So this is done with a specific solvent, and you can mess with the different ratios of polar to non-polar solvents to make the perfect eluent to get this kind of separation. So if you had this clear separation on the TLC plate, then in theory what you should get the same separation in a column, which means that it'll be very easy to collect them in two separate beakers or whatever container you're using. Oftentimes it's just a test tube. Okay, and so the explanation as to how, more or less, how the TLC works will come in the following video of where I actually do the experiment. And so if it doesn't make sense, if you understand this, then use the information that I've given you for the column chromatography and directly apply it to the TLC. So there's a stationary phase and there's a mobile phase, but the only difference is that the mobile phase travels up the stationary phase as opposed to down the stationary phase. And that's going to be it for column chromatography as well as TLC, thin layer chromatography. So I hope you enjoyed the video, and I hope it was really helpful, and I also hope you enjoy the experiments that you will perform as well as the one that I perform. Okay?